Extreme value theorem. If a function f is continuous on a closed interval ab, then f has an absolute maximum and an absolute minimum on ab. So to understand this theorem, we need to understand what are the conditions. So first, we need the function is continuous. Second, we need it to be on a closed interval, not an open interval. Then the conclusion is it will have an absolute max and absolute mean. So you take a look at a picture trying to understand this theorem. Okay, so this is an interval AB. Now because we want a continuous function, we have to draw the function without lifting our pen. Okay, so this is a function. We might notice some, okay, so if you can also call this interval AB an interval I. And by the definition, so don't get confused with absolute maximum and absolute minimum. On this interval I, which is AB, we definitely see the absolute minimum right here, the lowest point. Okay, so that is a absolute minimum. And the absolute maximum is the highest point right here. Okay, so that's an absolute maximum. You might see some local minimum or local maximum. What it is if you look at an interval inside I. So if you look at this interval, okay, so you look at this area, you see a local maximum. What it is the nearby point. If you evaluate the function on the nearby point, then the tallest, highest point is this purple one. Okay, so this is a local one. And this could be a local one on this subinterval of I or open interval of I, but also it's also the absolute maximum. So this is a difference between absolute and local. Local, you look at a small area of the interval, but absolute, you look at the entire interval. The lowest point is absolute mean, and the tallest point is absolute max. So this is an extreme value theorem. It tells you that you definitely will be able to find a point in A, which is this point, which is your V, such that f of V is the smallest. And you can find a point U right here in AB, such that f of U is the absolute maximum. So in order to find absolute value, okay, sometimes you might see the definition of critical numbers. So a critical number of a function f is a number c in the domain of f for which either f prime of c equals 0 or f prime of c does not exist. So this is a definition of critical number. How do you find it? On the other hand is that, okay, you find out what's f prime, you set it equals 0 and solve for c, or you find out where f prime of c is undefined. That's how you find a critical number. But that critical number is going to help us to locate the local minimum and local maximum because of this theorem. If f has a local minimum or local maximum at x equals c, then c must be a critical number. So what it is local extrema occur only at critical numbers. However, on the other hand, critical numbers does not mean it's a local maximum or local minimum. Okay, so on the other way, if you find out a critical number, doesn't mean it's going to give you a minimum or maximum. Why? Take a look at this counter example. f of x equals x cubed. It has a critical number, x equals 0. Why? Because f prime of x equals 3x squared. And when x equals 0, f prime of 0 equals 0. Okay, so 0 is a critical number, but 0 doesn't give us a maximum or minimum because f of 0 is neither. If you take a look at the graph, okay, it's just a point right here. So critical number can help us locate extreme value, but you still need to verify it is an extreme value by looking at the graph, but at least it gives you some point to look at. So now we take a look at example 1 to find critical number, if any, of the function. Okay, so how do we find critical number? We look for f prime of x. Now, because it's a piecewise function, we have to take the derivative in two different regions. One is in the interval includes 0 but exclude 1. Okay, so first piece, f prime of x equals 14x. Okay, so we take the derivative of 7x squared. So in this case, when will 14x equal 0? Is when x equals 0. Okay, we divide both sides by 14. So x equals 0 is a critical number because it's also in this interval. So now let's take a look at the interval 1, 2 inclusive. Okay, so f prime of x equal, so what is that? Is derivative of 5 minus x squared. It's just negative 2x. So when is negative 2x equals 0? Is when x equals 0. Is x equals 0 belongs to this interval? No. So x equals 0 is not a critical number on this region, but it is a critical number in this region. So overall, x equals 0 is a critical number. But do not forget, critical number also involve when f prime of x is undefined. So when is f prime of x undefined or does not exist? It's when f prime on one side does not match with f prime on the other side, or when the function is not continuous. So if you take a look at this function, okay, the only possible point that's not continuous is at x equals 1. So when x equals 1, okay, limit as x approach 1 from the left, well, less than 1 but approaching 1, we plug in the value right here. 7 times 1 squared is 7. But when the limit as x approach 1 from the right, f of x is 5 minus 1 squared, so it's 4. So the left side limit does not equal the right side limit. The limit does not exist. And when the limit does not exist, f is not continuous at x equals 1. So at x equals 1, the function is not continuous, therefore it's not differentiable. So f prime of x does not exist. So x equals 1 is also a critical number. So what are the critical number for this function? We find 2. Okay, one is 0, comma, another is 1.